Oh man, this paper was not fun to read. Usually I enjoy reading through papers, but this one was not very fun to read. Anyways, aside from my personal note on it, I do think it's a really cool idea, what they do in this paper, and I kind of want to go through how I think it's working. Um, that may be different from how it actually works. Uh, However, I have at least convinced myself that that is how it works. So I'm going to try to go through how I think that this paper is working. I've read through the paper, and it's difficult, but I think I have an idea for how this model is working, and I kind of wanted to show that. However, if I'm completely wrong with how it works, then yeah, let me know, and I would love to hear uh, how it works exactly. So yeah, uh, I suppose let's just get into it. So what is this paper? This paper is called Bayesian flow networks. So the idea with this paper is it kind of it introduces this new model that's similar to diffusion, but it's also quite different from diffusion, which we'll see. But I think one of my biggest problems with reading this paper is that I kind of thought about it as diffusion, and that made it difficult. Yeah. But first off, just as a basis, what is diffusion? And if you already know that, go ahead and skip this. But what is diffusion? So a diffusion model will take in some image. So draw, say, an image. We'll go with a good old cat. So there we go. We got a cat. So the diffusion model will take this image and it'll add a little bit of noise to it. So let me add some noise to this image. There we go. And add a little bit of noise, and there we go, a little bit noisy image. So this may be time step is equal to 0. This may be time step is equal to 1. And a diffusion model will do this for theoretically infinite steps. However, you don't need to do it for infinite steps, and it goes to a high enough amount of steps so that the amount of noise in the image after you continuously add noise to the image goes to basically pure noise. So at time step 2, there's more noise than time step 1 because more noise was added to the image. And then you keep on going until, like I said, you end up with an image that is all noise. So there's no image left in this image, and it's pure noise. And this may be time step, say, 1000. 1000 is generally reasonable if you're making this a discrete process. But then what you do is you train a model to reverse this noise. So it takes in this image with 100% noise in it, and it'll reverse it to the previous time step. I guess it's better to show it here, but it basically takes in any image at any time step, and it predicts the noise in that image. So say at time step 2, we give the model this image, and it basically predicts all the noise within this image. So let me see if I can get that. So at this time step, maybe it predicts that. There we go. So we throw this through a model, and the model predicts all the noise within that image. Then what we can do is we can remove part of the prediction so that it goes to the previous time step instead of going directly to time step 0. So in practice, you have the model predict all the noise in the image, but you only move it a little bit along the process. And you can think of this as it only predicting the noise within this image because there's going to be some error. And that's what allows diffusion to be really powerful, is you can just, you don't have to predict this first image altogether. Instead, you can predict an image in the previous time step, which is a little less noisy. and then you do it again, which is a little bit less noisy, and you do this 1,000 times, and it's an iterative process where you're basically removing noise from this image. So you add a bunch of noise to the image, and then you train a model to slowly remove the noise from the image. And yeah, that's how diffusion models work. And if you train a model on enough images for long enough, then you can sample some noise, some random noise from a Gaussian distribution, and you basically just let the model do whatever it wants with this noise, and it'll go along this trajectory and end up with some picture, whatever that may be. And since a Gaussian has theoretically infinite values it can take on, then you give it this and it'll generate a different image every time, unless you train it on the same image. But yeah, if you train it on a large enough data set, you give it some Gaussian noise and it'll generate a different image every time. So that's a diffusion model. And I think like this, they mentioned this in the paper as well, that this is basically the closest thing that is to their model, where the big idea is you have this iterative denoising process. So this part here, you can kind of think of it as like, so we have this Gaussian here, and let's say we have our data distribution here, which I'm going to just draw as a Gaussian. You can think of sampling this from a diffusion model as, let me draw this in blue, as taking a sample from this Gaussian, well, it would be this point here, and then moving along this process in some way. This can be a stochastic process, or it can be a deterministic process, depending on if you use an ODE or SDE solver. It's besides the point. And you end up somewhere on your data distribution here. And this data distribution is really simple. Obviously, it is a single value. It's not a bunch of values like this picture of a cat. So it's a single value here that is being predicted. But you can think of it as going from a Gaussian or a multivariate Gaussian, and then ending up on somewhere in this output on your data distribution. So this is your normal distribution, and this is your data distribution. And this is your backward process. This is your denoising process. Your noising process is the opposite, where it takes a value and it's usually an SDE, so maybe it's a little bit more noisy, and you end up on some part of the Gaussian. So the forward process is where you go from data to Gaussian, which is this to this. And the reverse process, which you teach the model to do, is take this noise and go to the data. Now, this is basically a single point to a distribution. Bayesian flow networks, on the other hand, go from distribution to distribution, and the model is predicting distribution to distribution, not distribution to data. If you can kind of see it, the model here is predicting, it's basically given this distribution, which ends up being an observed point on the distribution, on the normal distribution. It predicts some point on the data. So it's going from normal distribution to single data point. On the other hand, Bayesian flow networks go from normal distribution to data distribution, and it slowly converges on a point. So yeah, that's what happens with the Bayesian flow network, and I'll show you kind of how that works. One benefit to this is diffusion models do not work well with discrete data at all. Like if you had some buckets here of data, then mapping a Gaussian to one of these three categories, maybe this is like a large language model where you want to predict some words, and you have this distribution with three words, I guess, A, B, C, and you wanted to predict one of these words. Diffusion models do not work well with that at all, but Bayesian flow networks do, and it's a little confusing how it does that, but they are able to model discrete data a lot way better than they can model or than diffusion models can. So it's a big benefit. And they're also a lot different. So anyways, yeah, let's get into how Bayesian flow networks work. So they have this annoying Alice and Bob analogy, which feels like it just gets in the way. I also don't find this picture that helpful. A lot of the other ones are pretty helpful, but this one here, I feel like it confused me more than it should have. I'll get into some of the parts with what I think is good about this and what I don't. Because it does show a few things that I think are important, but other than that, I don't think it's that useful. So I'll just draw a diagram showing how I think that this model goes through the inference process, because I think the inference process gives the best idea for how this model works. And then training is pretty intuitive. I think once I show the inference process. So to start, we have let's do a single distribution. Let's do a distribution over a single value. So it's basically mapping a normal distribution to a distribution with just one value. So maybe that's like you have an image, maybe it's this top leftmost part of the image. And you can generalize this to as many values as you want if you just make it a vector of values as opposed to a single vector. So we're going to do a single distribution. And we're going to call, so they call the parameters theta, and I don't want you to get these confused with the parameters of the model, which are usually shown as theta. So yeah, these theta are not the model parameters. It is the distribution parameters of the data that we want to predict. And instead, I'm just going to use mu to not make that, to show that it's different. And then you also have a standard deviation, which can, like in a diffusion model, you can just get the standard deviation from the current time step in the diffusion model. If I go back to the diffusion model, this has 0 standard deviation, and this has high standard deviation. Maybe that's 1, depends on what type of model you're using. And anywhere in between there is, it's just an interpolation between sigma is equal to 0 and sigma is equal to maybe 1 or whatever you want to use. So same thing here. Now, step 0. So your initialization is initialize your parameters, your distribution parameters, to a normal distribution. Well, yeah, in this case, we're doing continuous data. So this is a normal distribution. And you're going to have your mean at 0. Mu is equal to 0. So this is your normal distribution that we all love and know. We love good old Gaussian distribution. And let's say we want to predict the value that the actual mu be equal to negative 0.5. So basically, we want to predict the value negative 0.5. And the value we start off with is basically saying we don't know anything about the output data. We are totally uninformed about the output data. We don't know it's supposed to be negative 0.5. We don't know anything about that. So I'm going to initialize it to a normal distribution, and basically we're going to kind of shift this distribution in ways to get more towards negative 0.5. But as we shift it, since we're more certain with our estimate of the single value we're trying to predict, then this mu value, it's shifting, but the standard deviation here, it gets smaller and smaller until it converges to, say, 0 or a value close enough to that, and you can just take the mean. So I didn't write 0. That's step 0 there. Now step 1. So step 1, so we have multiple parts, and you can think of this as the first step in the diffusion process. So step one is the model, or the first part of step one. Yeah, I have enough room. Is the model predicts the output distribution. So it predicts the output, what they call the output distribution, which is the data distribution. The data distribution we're trying to predict here. And they say it has some accuracy, alpha sub t, at time t, obviously, at time t. So this accuracy parameter is basically the variance that we're going to have. And you initialize it with really high variance. I think it's 1. I think 1 variance. So it initially has really high variance because we are uncertain what our data is. And they call this the accuracy. And you can think of this as the noise scheduler in the diffusion model. So they call this the output distribution, x tilde, and it has this distribution x tilde. This distribution, the output distribution, p sub o, is parameterized by a model, which is this Greek letter. I'm not going to try to. I forget what that Greek letter is. This Greek letter here, and the Greek letter takes in, or the model takes in theta, which I renamed to mu. So it takes in mu, which is our current estimate of the data and the time step. So it takes in the current time step and it takes in the current estimate of what we think our output data is going to be. And then it makes a prediction. And I can draw that over here. So we start out with this. This is our initial estimate. Mu is equal to 0. And this is our initial. And maybe the model says it makes a prediction. I will draw that a little bit over here. Maybe it makes a prediction mu is equal to -1. And in this case, it's not mu, it's x hat, and we do sample this. So x hat is sampled from here. So the model makes a direct prediction, basically, and this is the prediction of the output distribution. My idea of this is like, this is what is predicting the output distribution, but since we don't have any idea what the output distribution is going to be, it kind of has an idea for what it may be, but it's a very, very noisy idea, and you make it noisy in the way you train this. So it's kind of a noisy estimate of the model's first guess at the output data. So you have this guess. Now the output, the second step, or the second part of the first step, is the output distribution is converted to the receiver distribution. So receiver to the receiver distribution, and the receiver distribution is we'll get into the receiver and sender part in a sec, but it's or whenever we get into the training part. But this is the predicted sender distribution. So we convert the output distribution. This is our output distribution. I'll call it output. We convert this output distribution into the receiver distribution. Into the receiver distribution. And you do that by converting it. Converting to a normal. Given mean x hat, which is p. So probably this is our distribution, parameterized with x hat and alpha. And alpha is, remember, our accuracy. So at this time step, since it's the first step, alpha sub t, since it's the first step, this is going to be very high. So this is a normal distribution. Let me write it out here. Normal distribution, x hat, given theta t, and that. So it's the inverse of alpha. So I think I kind of messed up on how I said alpha. So alpha is your accuracy. This goes up to, this can be a really high value. And you start off with like, you don't start off with 0, but you start off with really low value. That means you have high variance. So maybe this is 1 over 0.00001. So this is going to be a really high value, and that means you have really high variance. And as you increase the number of time steps, you increase alpha so that it becomes a value closer to, it becomes a smaller value. So maybe this is 1 over 1, and so on. Maybe you get maybe you get to some time step and this becomes 1, and then it becomes a normal distribution basically, and then you can keep on going and it gets closer and closer to 0. Maybe you get to like 1,000 and it's even closer to 0. So as you increase your accuracy or your number of time steps, the variance in your receiver distribution gets lower and lower. And it's parameterized by this value here. And I guess I shouldn't have drawn a distribution here. It's just it's a single value. So this single value is then converted to a normal distribution or a Gaussian distribution, which we can see here. So let me draw this as like a large distribution over a lot of points because it has really, really high variance. And it's centered at x hat is equal to -1 because that's what the model predicted. So now this basically says we kind of know where the data may be. So the data falls somewhere in this distribution. And we are very unsure where it is, and that's why we have the high variance. So then the next step is to sample P sub r. So we sample this distribution to get a new belief or prediction of real data x, which remember that was -0.5. So we take a sample. Let me do this. So we take a sample. Maybe that is like right here. We just sample this distribution. So I just chose some arbitrary spot, and that is our kind of our prediction. This is how we're going to update our model. Now, using Bayesian inference, you can update this slightly because now you're a little bit more knowledgeable of what your output distribution will be like. And that assumes that your model is trained well. So now that you've updated it with your real data, now that you have updated, or now that you've sampled from this distribution here, which was, remember, we had our model taken our initial estimate, it predicted some mean value, and then we added a little bit of noise, we made this normal distribution, and then we sampled part of this normal distribution to get a prediction which we're going to use to update our initial estimate. Now, you update the initial estimate using the Bayesian inference, which is why it's called Bayesian flow. And this is observation y, actually. So this would be y using the observation. So after you observe this distribution and sampled it, then you update your x, and it'll be, since we sampled some value, maybe -1.5 or something like that, then the distribution is going to shift to the left a little bit. So maybe we have our initial distribution here. This is mu is equal to 0. And this was our initial distribution. Now our updated distribution using our observed value, maybe this is mu is equal to -0.1. So we update it slightly, and we're still very unsure, so we do this more and more steps. Now, as you do this more steps, like I said, your accuracy gets higher, and you're more certain about what this value is going to be. So we take this value, negative 0.1, and we do this over and over and over again. So at step n minus 1, maybe you have a distribution, or maybe your prediction is like, your mu is now at like negative 0.45. So maybe it looks something like this. At step n minus 1, we want to sample for n steps, and maybe it looks something like this, negative 0.45. And it almost has zero variance. And then, or yeah, it's very close. I mean, you can't have zero variance, but I guess you can. You just have that exact value, but can't really parameterize it that way. Now, the last part will basically just say, you take this value, you put it through the model, and remember, the model is what predicts. It takes in your estimate, and it predicts the output. Now, since you're going to have basically no variance, like you're at the last time step, and there's no variance in your data because you're very certain what the value is going to be, you can just take the direct output of the model, which will probably be somewhere like negative 0.49 because it's not going to be exact. And this is your predicted value after n steps. And this has, like I keep saying, zero variance. So this is your value that you take as your estimate for mu. And this is a single value. Now, if we made this d, you would have d distributions together, and the model would instead predict d output distributions instead of a single, or d output values, d means, instead of a single mu mean value here. So yeah, that's how they do this inference. So if we look here, they have this diagram here, and this is variable 1, so we're just going to look at this. Variable 2, maybe you have 2 means, and maybe you have more. So I think this diagram, what I think it does show well is how the, let me erase some of my scribbles here. There we go. I think what it does show well is how the loss is performed. So this may be 1. No, just leave it like that. So our output distribution, or our input distribution, is initialized to, in this case, it's a discrete case where you don't initialize it to a normal distribution. You initialize it to this distribution, uniform distribution. So you have this uniform distribution, and you give it to the model, and the model makes a prediction for what your output distribution is going to be. And your output distribution is obviously going to be some classification. Maybe this is over 3 words, A, B, and C. You want the model to predict B. So during training, they have this terrible analogy with Alice and Bob. I'm not going to use it. So during training, you have this data distribution and you have this output distribution. Now, you want the output distribution to match the data distribution. Remember, our model predicted, say, this value here. And this value is the estimate for what our actual data is. And if you say, and that's the direct output of the model. Remember that at the very end of inference, we just took the model's output and we said that was our final output. So we want that output to be as close to the data output as possible. So we want this to be as close to here as possible. Now, instead of optimizing that, and I think you can actually directly optimize these to indirectly optimize the loss. I think they go hand in hand, or to indirectly optimize the actual loss, I think they go hand in hand. But instead, they optimize this distribution here, which is after you convert this distribution to the noise distribution. So you take the output of the model here, and you convert it to a normal distribution. And you do the same with the data. And notice here how this distribution here is a normal. That's a normal distribution, and this is slightly shifted because of the category here. And these as well slightly shift the normal distribution. This is the categorical case. But you can imagine that we just had like one of these here. And this part here would be what we had on what I showed earlier. So the goal is to match these distributions here, and that indirectly matches the data distributions. And notice how they have this KL loss here. So that's your loss. And assuming that your receiver distribution, which is the noisy version of your model's output, is the same as the noisy version of the actual data, then you can make a good estimate here and sample this multiple times to like we did over here, and assuming that this does well, and or assuming that our model does well and makes a good prediction, then we can slowly converge on the data. And the reason they make it noisy is because we don't know what the exact value is. And notice that this prediction kind of sucked, but it does give you kind of an idea it gives you a better idea of what the data is, because notice how we started with no idea what it was, and maybe now we're like, okay, maybe we think it's A, but maybe we also think it's a little bit of B, but we know it's definitely not C. So this is the model's initial guess, and as you keep on making it have more and more guesses, and you keep sampling the distribution, assuming that it does well because the KL is similar, then you will converge on this data point here. So that's the idea. Just optimize the KL of the noisy output distributions. And I think that's pretty intuitive that you would want to do that. And the reason they do that is that you do discrete data. Now, the discrete data case is very weird. So I'm going to try to show how you would do that, the discrete case. It's slightly different from the continuous case, because the output isn't going to be the thing you're trying to predict isn't going to be easily defined by shifting a distribution around. Rather, you have these categories here, and you want to predict maybe this one here. So it's different. It's not the same. It's a similar problem, but not the same problem. So for the discrete case, let's say we start off with data. I'm going to change it from theta to mu again, so that I don't confuse it with the model parameters. This is data parameters, not the model parameters. So I'm going to call this mu1 and mu2. Actually, I do have to call these theta because mu is different. So we have mu1 and mu2. So you can imagine this as or mu1, mu2, and mu3. I want to do 3 values. So you can imagine this as a distribution looking like this, where this is mu1, mu2, and mu3, and this is just a value between, not mu, theta, where theta is just a value in between 0 and 1, somewhere in between there. And this is just your categorical distribution. And you have to define and this is how you parameterize it. Notice how it's different from how you would parameterize a continuous case. A continuous case, you can just use one variable, mean, and the standard deviation, which you can define by the time step, but this is different. And you also initialize a distribution that is continuous with and this is going to be a normal distribution. So this is an initialized normal distribution, and these are initialized parameters. And the initialized parameters can be uniform, or maybe they're not uniform, and maybe you use random values. So at step 0, let's just say some step. Let's say we start off with a distribution that looks like this. yeah, something like this. So this would be theta 1, this is theta 2, this is theta 3. Now at step 1, or the next step, the model predicts, so the model isn't given these theta. Rather, the model is given mu and sigma. So the model is predicting this mean and standard deviation of this continuous distribution, and we'll show how the continuous distribution kind of is going to be aligned with the categorical distribution. So the model predicts, maybe it predicts mu is equal to 0.1 and sigma is equal to 0.9. Now, this is kind of what you do with this data is you convert the, so as they showed up here, the model is going to make a prediction, and the prediction is the standard deviations from, it's mean and standard deviation, and you're going to use the input distribution to kind of form these Gaussians here based off this input distribution. So you're going to have you're going to have different Gaussians, and they're going to be different depending on what the output of the model is. And yeah, I'm just going to have a single output for the model, so it'll be one Gaussian that you're going to be shifting around, but they're basically shifted by the current theta. So, like if we had our thetas here, which may look like this. So I'm just copying it over here and making it sideways. Now, let's say we have our Gaussians here based off this mu and sigma. So 0 is down the center. Now, this first Gaussian will be shifted to the right. Well, all of them will be shifted to the right because this is positive, and we shift it to the right by this value here. So this is our Gaussian, and we're shifting it by the current thetas. So this may be shifted here, and this may be shifted more. So you can kind of see that they align with the values that we have for theta. This would be theta 3, theta 2, and theta 1. So these are our Gaussians. Now we sample distributions for each category. So we sample each of these distributions here. Maybe I sample it and I get the exact mean for theta 3, and I get something kind of on the right for theta 2, and I'm going to draw this a little bit, right here. There we go. And let's say I sample this one and I get something slightly off, something slightly to the left. Now notice how these aligned. I was doing that on purpose, but because it makes it easier to draw. So these are our samples. Now, what these look like are, so this is what our initial theta 1 looked like. This is our theta 2. This is our theta 3. Now, the updated values look like this, or something similar to this. Maybe you have, that's theta 1, that's theta 2, and this is theta 3. Or that's theta 2, and that's theta 3. So you take this distribution, the model predicts some values for the continuous distribution. You convert them to continuous distributions. You sample the continuous distributions, and then you get a new discrete distribution. Now, this distribution here is similar to, yeah, I would say that this distribution here is kind of similar to your output distribution. Yeah. So this would be, I would say this is similar to this distribution here, your output distribution. And then, yeah. So this is similar to your output distribution. And then we add noise to it to make it a receiver distribution here. And so we add a little bit of noise to it, and we convert this to some Gaussians, and you actually convert it to like the sum of them. I'm pretty sure for the discrete case. So the discrete case, it's strange. So you parameterize the normals with sampled data. So now we have this normal distribution, or we have this cumulative normal that's multimodal according to what we have up here. So you have, that's kind of theta 1, that's theta 3, and that's theta 2. Now your mean is kind of like our mean used to be 0. Now we sample it. Say we sample it and we get something here. So we sample it and we get our mean is equal to 0.75, something like that. Then you update so your belief is going to be updated where we're updating mu. We're not updating any of these parameters because these are discrete. So we're indirectly kind of updating these, because notice how our output does change the theta parameters, which is what we want to predict. And we kind of converted it to this continuous distribution from a categorical distribution, so we can actually do this Bayesian flow process in a continuous space. So once we sample it, we can update mu, and this is one step. So maybe we update mu from mu is equal to 0 to mu is equal to 0.1. Now you keep doing this, and since this is the output, this is your output distribution here. So you would sample this distribution here whenever you're done. And notice how this kind of shifted a little bit. This is going to keep shifting kind of like over here. And it's going to keep shifting, and you keep doing this, but we make it kind of a continuous process so that you can sample this output distribution in a categorical way, as opposed to not being able to do this because it's not continuous data. So I hope you can kind of see what we do here. We take the current belief of the data, we take it, we convert it to multiple Gaussians according to a model prediction based off our current belief of the continuous form of this data. We then sample that data, and that is our output distribution. And then we convert this to kind of a continuous form of the data. We sample this, we update our continuous form of this data, and then we keep doing this over and over again until you get your outputs here. So that's the discrete case. The discrete case is a lot weirder. It's a lot easier to understand the continuous case. So yeah. Now those are the two things that those are the two cases, discrete and continuous. If you're curious, they have all this math here, a ton of math. And they also have some code down here, some pseudocode here, which you can kind of see if, let's look at the continuous case real quick. So you have this, you initialize your belief to mu is equal to 0. So you have no initial belief about the data, no prior, well, I guess you do, you set it equal to 0, but basically no information. Then you predict, you make a prediction using your model, and you use this prediction to then parameterize a normal distribution where the accuracy is the inverse of the accuracy, so that you start off with a lot of variance and you end up with little to no variance. You then sample this data to get your kind of updated, you sample the data and then you update your belief about mu based off the sample of the data. And you keep doing this over and over again until you do n steps, and you keep updating your belief of the data, mu, and the output is you give it mu, and then you just take the direct output of the model, and that's your output, like I showed earlier. Finally, I want to go through some of the graphs. They have a lot of them. Some of them are pretty cool and just kind of cool to show off. The results are kind of cool. So this one is the Bayesian updates for continuous data. So you can kind of see, this is the start. The start is this black curve here. I do not need this side anymore. Let me get my highlighter out. So the start is this black curve here, and you can see it's centered at mu is equal to 0 with very high variance because we have no idea what the data actually is. Now mu is equal to 1. It takes, this is the distribution for mu is equal to 1, and then we basically sample that, and we get this point here. So then we update our belief, and now we have mu is equal to 2. So it's kind of moved over to the left a little bit because this is a sample that we took over to the left. So now we have this distribution, and it has less variance, and we sample it, and it moves over to the right a little bit. So then we now have a new distribution, and we sample it again. It moves over to the left a little bit, and we slowly hone in on the actual value of x is equal to 0.7. Notice how we're kind of shifting around it a little bit. So that's kind of what this is showing. It's showing that we slowly approach the actual distribution as we sample the predictions. Now this is also another way to show that. This starts off with very low accuracy, so very high variance, and that is this purple part here. So a very high variance here, and they have some other scheduler here, but yeah. This is where we start, and this is kind of a pretty cool graph, but it slowly shows that it slowly morphs into this the prediction that we want it to make here, which is x is equal to 0.7, and it kind of moves over here, and it slowly hones in on this value on this value here, and as the accuracy increases, the variance gets smaller. So I don't know, thought that was kind of a cool and interesting graph. Here, this is similar to diffusion. If you've seen pictures of diffusion, this kind of looks like an SDE in a way. So you start off with this value here. All data starts off with this value, and you slowly move over to the actual value, x is equal to 0.8 in this case, as you keep making predictions. And notice how it has very high variance at first, and as time continues, you get lower and lower variance as you hone in on the actual value of the data. This is showing the noise schedulers. This green and red are your normal diffusion schedulers, and they have a weird looking scheduler, which I guess they find works well. This is just output distribution, receiver and sender distributions. Not a big deal there. Yeah, so this is basically the conversion from a categorical distribution with parameters theta to the predicted, or to the distribution that goes along with that, given this mu. So you can see that it fits the data kind of well, even though you have this mode over here, which is a lot higher. So this kind of shows that you have this distribution that aligns with it well, and they have some more data down here showing that better. So you initially start off with this initialized data at some point in time, and they have here, the red is the sender distribution, that's what you want to predict, but so you have the discretized buckets here, and you have the output density, that's the output distribution from the model, as your green curve here. And the receiver distribution is the noisy version of your output of the model. It's more interesting in this case here, where green is your output density, that's your prediction, but then whenever you kind of combine the modes together, you get this blue line here. and you can see it kind of fits the data a little bit better, which is this part here. And it slowly fits the data more and more, so you can see it, that part there, to, I guess, what we wanted to predict was this mode here. So it slowly goes over to that, and this is kind of a cool visualization showing the distributions moving over to that. And if we keep going down, they have some more visualizations. And they also do this with the binary case, which is kind of interesting. And if we keep going down, they have some results. So let's look at this. Improved DDPM. That's pretty standard. 2.94 on CFAR10. And the Bayesian flow networks get 2.66. I think yeah. What is this? This is this, I don't know what, these just values? Comparison of dynamically binary with other methods. I'm guessing this is the FID score. So you want I think BFN does better in this case for, no, it does worse than improved DDPM, I think. Not sure, but it does at least similar with the DDPM, improved DDPM, which is very promising. Yeah. Oh, no. All right, so yeah, here we go. This is, we'll just go to the experiments to kind of show off the pictures. So you can see it does generate mist, which is a good thing to show off. If it could do mist, then it's a good first step. It is interesting to see. So this is the output distribution. So this is, the model takes in this input distribution, and then it predicts the output distribution. And it's interesting to see how it kind of flows. Some more results. Here's CFAR10 results. Looks like CFAR10. And this is also the this is the input to the model. This is the output to the model. Also interesting to see. And then they have text, which is something that diffusion couldn't do. So yeah, I mean, it can generate text that looks not like garbage, which is better than a lot of methods. It's better than any method that's not autoregressive, pretty much. And yeah, some more results. Yeah, it can generate text, which is cool. And I think that's it. Yeah. I think it'll be cool to see kind of where this model goes. It looks very promising. It looks like a very promising approach. So I'm very excited to see how Bayesian flow networks come up, like how they come about, and maybe they will beat diffusion models in some way, but they can do something diffusion models cannot, and that's discrete data, which is very cool to see. So overall, I'm excited to see how this model performs, and hopefully this explanation made sense. It was very difficult to read through this paper, and I hope I was able to help you out, kind of understand this paper a little better if it was difficult to understand when you read through it. But yeah, there we go. Excited to see how this model is going to work.